61. Sounds good anyway. Pretty sure we were on 60 yesterday. Okay, so before we had to rewind and go back to what I forgot to teach you, we had done the fundamental theorem of calculus, part 1. We spent a couple days on it, then you were able to do some AP classroom stuff. So here is part 2. All right, the second fundamental theorem of calculus. And I do want to remind you that when you have, remember if we have f, and then we would have f prime, and then we would have f double prime, right? So if we are going up like this, right, when you do your integrals. So if we went up from that, that's what becomes a capital F, okay? When we do our derivatives, right, f, the derivative of f is f prime, f double prime, but if you're taking the integrals and going backwards, if you have a little f, it becomes a big F. But if you have a big F, when you take the derivative, one of two things could happen. It could be the little f just like that, or we could use it as big F prime. Okay? So, just FYI. It's going to be that you see it more than you have to really, like if you do it, you can do it either way you want, but you could see both things, and I just want to make sure that those things make sense to you. All right, so let's say that we have some sort of graph, and it's whatever it is, doesn't really matter, and we have some interval going from a to x, okay? If I'm going to integrate that function from a to x, I'm finding the area under that curve, right? Going from left to right. So that's what's happening here. Take the derivative, not the derivative, we're taking the integral from a to x of f of x dt. But then if I turn around and take the derivative of that, it's like doing something and then undoing it, right? It's taking the integral and then taking the derivative. It's multiplying and then dividing by 2. Or taking the inverse of something. That's what inverses are as well. So this part is doing the integral, and then this part right here is undoing the integral. So when we do this, and I'll get to the why in a minute, but we're just going to see how to do this first. Notice that this is the derivative with respect to x, and there's an x with the integral, and then this is f of t dt. So one thing that's super important when these are written, or when you end up writing them, is that this variable and this variable cannot match. After you understand the concept a little bit better, I'll talk to you about why they can't, okay? I feel like if I explain to you why right now, it's just going to be too much. Okay, thank you. Wait, no, not mine. You're not even anywhere near the right room, so are you sure this one was for me? This is 115. Okay, I was going to say, you can't be that off. Yeah, there we go. This one. Okay, got it. All right. Here you go. Okay. So this says, do not leave if it's inconvenient for your teacher. I don't know what this is for.
Probably they want me to do the same jack application.
Oh, do you want to do it? Okay, that's what I thought. Okay, it's inconvenient for me. You're not allowed to leave. There you go. Okay, so when you do this, right, now what I was saying before I was so rudely interrupted by the knock, the variable that's with the integral and the variable in here, they have to be different, but I will explain to you the why. Right now, it's going to be because I said so, but we'll get there. So when we do this, whatever this variable is, which is x, a is some number, right? X is a variable. I just put that in there, and then this is just equal to f of x. So I want you to think about, I take 6, and I divide it by 2, and I get 3. Then I multiply it by 2, and I get 6 back, right? So I have this, I'm taking the integral, so I'm doing something, and then this undoes it, and I end up back here. And I'm just substituting it in there. Okay, does that make sense? Because integrals and derivatives are basically doing the opposites of each other. All right? Okay. But what? Right. But since we are integrating from a to x, we have to actually do something with the x. It's not exactly like dividing by 2 and then multiplying by 2, but you have to put that x in there, and that becomes f of x. You still have to, like if I was to actually take the integral, like literally do it, literally do this, then x is going to end up in there. And then when I take the derivative, it's still in there. Does that make sense to you? A little bit? Just hang on and it'll get a little bit better. That's a very good question. Okay, now what is the difference between the way this is written and the way this is written? The x from x to a. So on that first one, we're going from a to x, we're going to the right. So our area that we find is positive, right? If we're going from x to a, we're going to the left, what happens? It's negative. It changes the sign. So this, we still take the x and put that in there, but then this is negative f of x. So we're going to do a couple just to get the patterns down, and then we'll talk about why and what's really happening here. Okay? We all good with that? All right. So let's look at this one. I'm just going to take the x, and I'm going to put it in here. And then this just becomes x squared. It's whatever this function was, right? Just like that. That's it. Yes? So here, because it's an integral and a derivative, I really don't care what the derivative of cosine is or the integral of cosine. I mean, I could do it and then undo it, but all I'm doing is this is where my x is. My x goes in right there, and my answer is cosine of x. All right. Then this x goes in here. Is my answer x squared? No, it is negative x squared. Or is it negative x squared? Which one is it? It's the first one, right? Because it's the function and we make it negative, so it's definitely not that one. Now, any questions about what is or isn't happening here? Because I would think you might have some at this point. Like maybe, what the heck is happening to these numbers? Yeah? And why, do they just not matter? Are they just disappearing? Is there some sort of magic going on? Like, what is happening, right? Very valid question. So let's go look at this. Why does it work? Because this is a very simple process. Would you agree with that? It's pretty simple, okay, if you understand what the heck's going on. So let's look at why it works. This says we're going to write an integral involving s of t, the position of a particle at time s, after it starts to move, given a velocity function v of t, and an initial condition s of 0 equals c. All right, so how are s of t and v of t related? Okay. Position, velocity. So position, velocity, acceleration, right? So this is s prime, and this is s double prime, right? So velocity is the derivative of position, yes? Okay. So it says write an integral equation involving s of t, the position of the particle. So we're going to use the first fundamental theorem of calculus, the one that we learned the other day, which is going to be the integral, okay, from 0 to t, because this is using a t in here, of v of x dx. Now the t and the x are switched from up there because in my final stuff I'm actually using a t. So I could use x, I could use u, I could use literally anything except for t. They have to be different. And again, just trust me that I will explain to you why, but I think it will help if you actually know what you're doing a little bit better. If I integrate velocity, I'm going to get position, right? And then, so what your fundamental theorem of calculus says is the integral is then going to be s of t minus s of 0. Right? Do you remember that? Let's rewrite that as, probably should, I'm going to rewrite that but not as big so I can write something next to it. If you wrote big, it's fine, but I just want to make sure. I'm going to rewrite the exact same thing. There was nothing wrong. The integral from 0 to t of, there's something wrong with it, v of x dx equals s of t minus s of 0. All right, so the fundamental theorem of calculus says if I have this from a to b of f of x dx, that's equal to f of a, f of b minus f of a. So that's what it looks like with the f's. That's what we talked about the other day. So the integral, the area under the curve, the accumulation, that's what this is. It's the final minus the initial. Then you know how much was accumulated, right? Okay, so this is basically the same thing, but with b's and s's and the t's and that sort of thing. So now, if I take the derivative of both sides, so we are going to write a little bit more than we normally have to, just because I want to make sure that you understand what's happening here. d dx of, well, I don't have that. Let's just do this. The integral from 0 to t of v of x dx equals, and then so if I'm going to take the derivative of one side, I have to take the derivative of both sides. And then this is going to be s of t minus s of 0. So all I did was just add, basically showing my work. I'm going to take the derivative of both sides. That's it. So when I do that, over here, I'm just going to rewrite this. D dx, the integral of 0 to t of v of x dx equals, so then when I take the derivative of this, what is the derivative of position? What's the derivative of position? Velocity. So when I take the derivative of this, I get v of t. When I take the derivative of this, it tells me right here that s of 0 equals c. That means a constant. What's the derivative of a constant? 0. So that's really minus 0, and I don't even have to put anything. And then this right here is what we were doing up there. This was the question that we had. We just take t and put it in here, we end up with v of t. That's why it works. We're taking the fundamental theorem of calculus and taking the derivative of both sides. Okay? Would it help if I did it again with the f's? Okay. So I'm going to do basically the same thing, except apparently I'm going to have to write a little bit smaller because I don't know why I write so. I'm going to take the derivative. So d dx, the integral from a to b of f of x dx equals the derivative of this side, which is f of b minus f of a. Oh. Okay, so one thing we want to change in this, when we do this, and now we're having it with an x in here instead, then when we actually, this is the fundamental theorem of calculus, I'm going to change this b to an x. I'll use a better color, x. And I'm going to change this b to an x, because it's not an actual value that I know. A is a value that I know. So f of a is just going to be some number, but those are going to be x's. And if I do that, this has to be a t. Okay? Sorry, we could have rewritten it again instead of me writing on top of it, but I just want you to see that that's what's happening. If I change this to an x, this can no longer be x. As soon as I change this, this has to change to something else like t. Or u, or whatever. T is just kind of what's normally used. So then, when I take the derivative with respect to x of the integral from a to x of f of t dt equals, well, the derivative of capital X is lowercase x. Oh, sorry, capital F is lowercase f. And then this is just a number, so that's just going to be my 0, and that's right there is your second fundamental theorem of calculus. That's why it works. Okay? Does that help? Okay. I know. I didn't love that. I mean, I get that this example, we're trying to understand the F's and the S's, but I think first example probably should have been done with F's. So I think we'll probably redo the second one differently too, just because I think it'll be helpful. All right. What questions you got? We good so far? All right, words of warning. And this is the variable of integration the dt of the problem must be different than the variable found in the limits of integration. Okay, so the long s. So this variable has to be different than this variable. And I'm just going to keep repeating that, and then once we understand it a little bit better, I'll explain to you why. I'm just afraid that it'll get... Sometimes when I explain things on the whys too soon, then you try and start doing that in your work because you remember seeing that, and I don't want that to happen. Okay. Everybody okay so far? All right. So, continuing on. Here is the fundamental theorem of calculus part 2 with the chain rule. Do we remember having a chain rule? Okay. So notice that instead of going from a to x, it's going to from a to g of x. G of x could be anything. It could be x squared. It could be 2x. It could be really just anything. Anything that's not just plain old x. Some sort of function. Okay? When that happens, you still take this, pretend like it was x, you put it right in there where t was, because that's what happened right there. And then you take the derivative of whatever you put inside of f. It's that simple. Yes, I know, I was kind of waiting for that. So on the other ones, if this was x, we took x and we just plugged it in there and we're like, boop, we're done, right? So we still take whatever this is that'll have an x or some other variable in it. We put it in here. That's what this is. But then because it just wasn't plain old x right here, we take the derivative of whatever that thing is. So for instance, we're going to take x squared and put it in there where that t is, yes? So this is going to give me cosine of x squared. But then I also have to multiply it by the derivative of this, which is what? 2x. And you're done. You can leave it like that. If it's written for you, then it would actually probably look like 2x times the cosine of x squared. But you don't have to write it like this. This is fine. I wouldn't bother fixing it unless you need to and it helps you somehow. Okay. How are we feeling about this so far? Good? Okay. Bad, not bad. All right, let's look at A. Do we have to... Okay, so we're going from 3 to x. So if x is on the top, we don't have to worry about a negative anywhere, right? Then we take whatever this is, and it goes in right where the variable goes. So this is just going to give me the square root of 1 plus x squared. Do I have to take the derivative of anything? No, because this is just plain old x. And if it's plain old x, then we're good. Okay? What? Be under the square root more what? No. Because if we had, so here's your question. That's a good question. Since it's under the square root, wouldn't it make it chain rule? And the answer is no, because I'm not actually taking the derivative of this. It's whatever this is. And since this is plain old x, it just plops in there. If what I put, and yes, there's other stuff under there, but I didn't put it there. It was already there. If I substitute it in and it's more than just x, then I have to do that. Yes. Okay. Does that make sense? We good on that? Okay. All right. Uh-huh. I think if it's given to you, it's going to be a t probably every time. If you had to set it up, then you could use any variable as long as it's not what you put in here. Okay? So yeah, you'd be fine. I would not choose O because it's going to look like a 0, but really any other letter, or an L because it'll look like a 1, but other than that, you're probably fine. But you'll see T every time, pretty much. Okay. All right. So let's do the left-hand side here. This is in here twice. We're going to do this twice here. So tangent, what do I do with this x? Substitute it in here, right? And then that's going to give me the tangent of x cubed. All right. Do I need to take the derivative of x cubed? No, because we put x in there, right? since it has based on this, we put x in there, just plain old x, so we're not taking the derivative of it. Yes? Okay. And then this equals, now this part's the same, right? But what's different? The x is down here. So what do we put on this side? Negative tangent of x cubed. Do I need to take the derivative now? No. And we're done. And if you didn't know that tangent of x cubed is equal to negative tangent of x cubed, now you do. Okay? It just works that way. That's because tangent is positive in the first and third quadrants, and so they are across from each other. That's why things like that work. Okay. And notice again, this 3 and this 2, we just completely ignored. Okay? So don't try and do anything weird with those. Let's look at C. Okay? I'm going to take this x cubed, and I'm going to put it in there where that t is. And this is going to give me 1 over 1 plus x cubed. Now let's talk about what we take the derivative of. We do not take the derivative of this entire thing. We do not take the derivative of the denominator. We take the derivative of this. So what is the derivative of x cubed? 3x squared. And then you can just leave it like that. Okay? Don't try and go just taking the derivative of all kinds of things. It's the derivative of whatever this is. You substitute it in just like you did on all the rest. Whatever it is, you just plop it in there, and then you take the derivative of whatever that was. All right, so you try D. Yes. That's what I got. Oh, okay. This? Okay. Yes. If you write it like this. If you write it like this, you're fine. Here's what is not okay. Root of 1 plus sine of x squared. That's a big fat no-no. Okay? Well, even if the 2 is in the parentheses, that's still a big fat no-no. Okay? Cosine. Not a skinny one, a big fat no-no, yes. Okay. So this is really how you write it, but this is okay. This is not. Do we understand why it's not the same thing? Okay. It's the sine, because you're doing the sine of x squared, not the sine of x squared. Yeah, right. You got that now? Yeah, fine. Good. Yeah, sure. I never know. Never know with you. Okay. So then here's where I'm going to explain the second fundamental theorem, but since we only have 4 minutes left, I do not want to do that right now, because I don't want to get in the middle of it and then really confuse you. But I am going to give you the next page of notes just in case you're not here tomorrow, because you will be able to work through these without me. And remember, you need to get your AP class, I don't know why I can't remember what it's called. AP classroom stuff done. If you get like a 1 out of it, I'm going to think you didn't even try. If you got most of them right, half of them right, then I'm going to say, okay, at least they tried. And I'm just going to trust that you actually tried. Okay, because that's what I want. And I want you to go back, and the ones that don't tell you why it's wrong or whatever, see if you can figure out why it's wrong. And then if you still can't, let me know, and we'll all talk about it, because we probably all need to talk about it. Okay?